Hello everyone, I'm Bo Xiaoyu. Today I will introduce the course project of my image processing and computer vision class. The topic of my project is research on influence of different image processing on the results of link-keeping model. I will introduce my project from the following three aspects: introduction, implementation, conclusion, and analysis. First, let me introduce the problem I'm researching, and then briefly introduce my solution process. So the problem is that can proper image processing of the input data set improve the results of the link keeping system? That is, for the link keeping model, if I do some processing on the images of the input data set, will the accuracy of model prediction be improved? To explore this problem, I did the following research. First, I built the baseline link keeping model and obtained the benchmark result. Then I apply several different image processing techniques to the original data size. These image processing techniques are from the image processing and computer vision lectures and relevant papers. At last, after I got the new processed dataset, I retrained the model with them and compared the result with the benchmark result. So let's get started. Self-driving cars are an important development direction for future road vehicles. Among them, the task of lane keeping is a key issue for realizing autonomous driving technology. This project would focus on optimizing the lane keeping model. In the research of lane keeping, the traditional methods to divide the task of lane keeping into multiple parts, as shown in the middle figure, such as lane marking detection, path planning, control logic factory, and each part is studied separately. The performance of this traditional method is highly dependent on the feature extraction of image data, coupled with manually defined functions and the accumulation of errors in each research part. The complexity of the traditional method is high, but the accuracy is not performed such well. The end-to-end supervised learning method treats the entire mapping problem from the input road image frame to the output vehicle steering angle as a single indivisible task. This end-to-end method reduces the manual workload and can get very good performance. So the baseline model adopts an end-to-end supervised learning method. The lane keeping task is realized by taking the actual road driving image frame, as shown in the left figure as input, using an end-to-end learning method, and directly outputting the steering angle of the vehicle after model training, as shown in the red table. So that is directly guides the vehicle to steer through the front view camera data after completing the training and completes the lane keeping task of the self-driving cars. These are some image processing techniques that I have learned in class, and also some related contents in abstract papers, which I think may be proper to optimize the data set of the lane keeping model to get better accuracy. So above are the research background. Then let's focus on the specific implementation. The dataset for this project is the Tesla open source data obtained from the Open Source website. The open source data contains two types of data. One is a sample of the video frame taken during actual driving, as shown in the upper right figure. The video frame is a front view image taken by a camera installed in the center of the vehicle. The picture contains the front of the car at the bottom, the lane markings on the road, and the sky in the upper half. Many of them are useless information, like the front of the car and the sky. The other is a CSV file that records the steering angle of the steering wheel along each frame of the video. As shown in the table on the left, the first column is a timestamp. The second one is corresponding video frame number, and the third one is the corresponding wheel steering angle. Then the NVIDIA model is used as the benchmark model for training. This is a regression problem using MSE evaluation indicators. The results are shown in the table. From the last test loss, we can obviously observe that YUV model with shuffled data input can get the better result. I also realized the result of pre-training and test. As shown in these 4 pictures, we can also observe that YUV model with shuffled data input can get better results. So I set this as the baseline model. After building the baseline model, I started to process the image frames of the input video. First is a transform video encoding format. The video format in the original dataset is the MKV encoding. In general, MKV has better quality, but the file size is larger and compatibility is slightly worse. On the contrary, files in MP4 format are easier to store and easier to operate, although the quality is slightly worse. It basically meets the image quality requirements of model training. So in this project, I first convert the original MKV encoding format to MP4 encoding format. The left image is an example of the original video frame sample, and the right image is encoding transformed video frame sample. After the coding format, the number of and size of the image frames does not change. Image construct refers to the measurement of the different brightness levels between the brightest white and the darkest black in the bright and dark areas of an image. That is the size of the grayscale contrast of an image. The larger the difference range, the greater the contrast. The distribution of clear images in the color histogram is more even. If an image has a longer span on the histogram, it means that the more gray values used in the image, it can be more clearly reflect the direct difference between every detail in the image and the details around it. On the right side of the original image is the sample frame after image contrast enhancement, and the right side is after the image contrast reduction. I'm sorry, the left side. Image quantization is the process of converting the continuous change interval of the corresponding brightness of the image pixels into a single specific value. That is, discretizing the spatial coordinate amplitude value of the original grayscale image. The more quantization levels, the richer the image levels, the higher the grayscale resolution, and the better the image quality. On the contrary, the image contour layer phenomenon will occur, which reduces the image quality. The image on the right side is the image frame after gamma quantization. Then is image sharpening and image smoothing. Image sharpening can compensate for the outline of the image, enhance the edge and the part of the gray transition, and make the image clearer. The purpose is to make the edges, contours, and details of the image clear. The right side of the original frame is image after image sharpening, and the left side is the image after image smoothing. Then it's a grayscale image. We have already done similar content in our assignment 1, so I don't gonna talk more about it here. The last is the adjustment of image brightness, which is the most basic and critical technology in image processing. The right side of the original frame is the image after brightness enhancement, and the left side is the image after brightness reduction. Okay, so let's have a look at the code. Here are four baseline code, which are using RGB mode and UV mode and other data and shuffle data. And this is for RGB mode. We can see that this used shuffle data here. Oh, this is YUV mode with older data, and this is YUV mode with shuffle data. And finally, I choose the YUV mode with shuffle data set to the baseline model. And it will output a visualized image. And here got the test loss. And these are programs with different image processing. Like this is for image contrast enhancement, and this is for image contrast deduction, and this is for the image quantization, and this is a gamma quantization, and this is for grayscale to output the grayscale video, and this is to adjust the brightness for the video. And yeah, this is transform the video transformation from MPV to MP4. And okay, this is the image smoothing and the image sharpening. Here, output the image frame. And after I run the baseline model code with different data set, I can get the process of training and the final test loss. Here is the training loss, and this is the valid loss during the training process. Okay, let's go back to the PowerPoint. So far, I have introduced the baseline model and the optimization of the dataset through image processing. Now let's focus on the results. I refed each image processed dataset into the model for training and got the result of the training process and the prediction result. These non-pictures are the distribution of training loss and value loss using the original dataset and the optimized dataset. It can be seen that they are all basically gradually approaching to zero. Then these are the specific training loss, value loss, and test loss corresponding to each type of data. By comparing with the baseline, we can conclude that the applying video encoding transform, image sharpening, rescale, scaling, and brightness enhancement techniques can improve the accuracy of link keeping model. But here's a problem. In theory, image contrast enhancement can make the raw line in the driving pictures clear so that the model has a better performance in the feature extraction part. But judging from the test loss, the result does not match. After reviewing the problem, I found that in the process of training this dataset, the training loss reached a very low value, while the test loss have a very high accuracy of the model. From this, I made the conclusion that application of image contrast enhancement technology to the dataset is not that the accuracy of the model cannot improve, but that overfitting occurred during the model training process. So those are the work I finished and the results I have obtained in this project. I do have completed the preset task of link keeping for self-driving cars and improved the accuracy of the model by processing the video frame dataset. Thank you for listening. These are all of my course project.